We'll keep praying that Prof's network improves so that he can join us.
mute I'm gonna I doing I'm gonna make our mute I'm gonna hang
Hello.
what you have to go so long please.
Prof is back. I can see his screen from here. Yeah, Prof is back.
So I can't go allow with in a question for opinion. If you want to ask question, you raise up your hand here. You raise your hand here. You raise your hand here. Pananga will say what's up there. Also contributing the okay, somebody angel.
Very please mute yourself now.
Sorry, sir. I've done that.
Prof, you have the floor now, sir.
Can you hear me now?
Yes, Prof.
Right.
Yes,
Okay.
Prof.
So,
Welcome, sir.
So we have been able to demonstrate the first property where if we introduce glucose in a pure water, and we saw that the vapor pressure of that solution decreased by 0.24. So, hi, come on.
Huh? I'm pumping on.
Simple courtesy demands that enter a Zoom meeting, you off your mic.
I have all characters of people here. You know, it's all right. So you see, we have demonstrated that the first property, that is the vapor pressure lowering, on introduction of glucose. That glucose was a solute we introduced in the solution, and we saw that the vapor pressure of the pure water or solvent decreased by 0.24. Don't bother too much. When we meet face to face, we still do some of these things in a much clearer way so that you understand better. So we are going to boiling point elevation. So that is what we are going to demonstrate now, boiling point elevation. So other boiling point elevation is a similar thing. When you introduce a solute, what you observe is that the boiling point of the solution increases or becomes elevated by a fraction of the temperature. So this one too, I want us to look at an example. So if you are with your writing material, you can take this down now. That's the question on boiling point elevation. Boiling point elevation is given by delta TB equal to KB times M, where KB is the boiling point elevation constant. That KB is known as boiling point elevation constant, and M, that is MU, is the molality. So the boiling point elevation is represented by delta TB. That B is boiling point, T is temperature. So it's equal to KB times M. That's why you have delta TB equal to KBM. Okay? So let's take one example and see how the answer is going to be. If you are ready, you can begin to write. Calculate the boiling point elevation. Are you there? Calculate the boiling point elevation. Hello? Hello?
We are with you, sir. We are with you, sir.
Right. Calculate the boiling point elevation of a solution made by dissolving 10 grams of sodium chloride. The sodium chloride here is the solute or the chemical or the compound that we are introducing into the water or into the solvent to give us a solution. So we want to determine the boiling point of that solution after dissolving the sodium chloride salt. So calculate the boiling point elevation of a solution that is made by dissolving 10 grams of sodium chloride in 100 grams of water. Dissolving 10 grams of sodium chloride in 100 grams of water. And I told you that KB is a constant. So anywhere you have a constant, it will be provided or given. The value of that constant will be given. So in this case, the value of KB, that B is a subscript. It's a subscript. KB is equal to 0.512. KB is equal to 0.512
We are with you, sir.
I'm trying to call the unit. 0.512 Kelvin, that is capital K. After the 0.512, write capital K, leave a space, then write small k, then small g, as Kelvin, kilogram per mole, then slash mole, MOL, for water. The boiling point elevation constant for water is given as 0.512 capital K, small kg as kilogram slash mole. That's a unit for water. And mind you, I told you that that small m that you are seeing there is known as molality. Molality is the same thing as just like we did in the case of vapor pressure depression. Here too, the molality is given as moles of sodium chloride divided by kilogram of water. divided by kilogram of water. Moles is equal to sodium chloride, that is the mass of sodium chloride, which is given as 10 grams. 10 grams, the 10 grams divide by the molar mass of sodium chloride. And the molar mass of sodium chloride in this case is 58.44. 58.44. Molality, that is small m, is equal to moles of sodium chloride divided by kilogram, which is equal to 10 grams divided by 58.44. You know where the 58.44 is coming from, I guess. That is sodium is 23, chlorine is 35.44 or so. 35.44. That is the mass of chlorine. So if you add, just like we were told the other time, that is sodium, which is 23, atomic mass of 23 plus 35.5 will give you about 58, thereabout. Yeah, 58. 23 plus 35.44 will give you 58.44. And the unit is grams per mole. The unit you are going to get is grams per mole. Grams per mole. So 10 grams divided by 58.44 divided by divide 10 grams divided by that. And mind you, the 10 grams is in grams. But you see that we have kilograms. We have kilograms of water. Kilogram of water sodium chloride, that is mass of molar mass. Then we have to convert that 100 grams. We have to convert that 100 grams. We have to convert that kilogram of water. That is 100 grams of water. We need to convert it to kilograms too. So if you divide that by 1,000, that's 100 divided by 1,000, you're going to get 0.1. 0.1. 0.1. 0.1. That will give you 1.71. 1.71. Mind you, number of moles is equal to mass over molar mass. So the 10 grams you divide by 58.44 is for sodium chloride. That is the number of moles of sodium chloride. So if you divide that again by 100 grams, which we have converted to kilogram, that is by 0.1. That will give you 0.1 kilogram in kilograms. You will get 1.71. Hello? So I mean, change in temperature now is going to be that constant, which is 0.512. 0.512, that is the constant KB, times molar.
Mistakenly do what? Yeah.
Hello? Hello? So hello?
Prof, we can hear you, sir.
Hello?
Hear you.
Right. So let me go back to the beginning because of the fluctuation. So we are looking at boiling point elevation, and we are asked to calculate the boiling point elevation of a solution that is made by dissolving 10 grams of sodium chloride in 100 grams of water. Okay? We have been given the constant, that is the boiling point elevation constant, to 0.512 for water. So we need to determine the molarity, which is that small m. and it is given by the moles of sodium chloride, okay, divided by the kilogram of water. So how do you determine the mole of sodium chloride? The number of moles of sodium chloride is given by 10 grams divided by 58.4 grams per mole. Mind you, that molality is given by moles, number of moles of sodium chloride. So the number of moles of sodium chloride is the mass of sodium chloride divided by its molar mass, which is 10 grams divided by 58.44 grams per mole. Now you are dividing that 10 grams over 58.44 by 0.1 kilogram. Why is it 0.1 kilogram? You are converting the 100 grams of water, the 100 grams of water to kilogram. So if you divide 100 by 1,000, you are going to get 0.1. And the answer is going to be what? 1.71 molality. 1.71. Now, what did the formula say? The formula says change in temperature elevation is equal to the boiling point elevation constant, which is 0.512 times the molality. That is that small m. And the small m is what? 1.71. When you multiply 0.512 by 1.71, you are going to get 0.88 Kelvin. 0.88 Kelvin. All right? So, and I said that water boils at 100 degrees Celsius. That is pure solvent or pure water. But the 0.88 that you have got is the elevation. So you now add the 0.88 Kelvin to 100 degrees Celsius. When you add the 0.88 to 100 degrees Celsius, you are going to have 100.88 degrees Celsius. Why? That has become your boiling point elevation value. It means that on addition of sodium chloride, it elevated the temperature to 100.88 degrees Celsius. Do you understand? Hello?
Yeah.
Hello? Did you get the point?
Yes, sir.
Right. Whether you got the point or you didn't get it, don't bother so much, because tomorrow morning, when our brains are going to be fresh, I will still go over it. Okay? So see how you can think about the whole thing tonight, so that by the time I refresh your brains tomorrow morning concerning this one, you will be at the same page with me. Okay?
Mm-hmm.
In fact, these notes need revision. That is why I'm not bothering so much on the notes here. Because if I say I will go by what you have in the notes here, you will get more confused. That is why I'm bringing a shorter way of doing these calculations. Okay? Not minding the other attachments that are involved. But don't bother, you will get the full dose of it. Probably when we are doing our last revision before your exams. So we'll be noting areas of difficulty, areas that you are having challenges, so that even on Friday, that we are going to conclude this course, we should be able to, raise some issues. So let's move to freezing point depression. Freezing point depression. Freezing point depression. Here, when you add a solute, it will depress or reduce the boiling point. I mean, the freezing point. Okay? So let's take an example. We'll take an example very quickly before it is 2 o'clock. After that, we'll take osmotic pressure and then maybe close for the day and continue tomorrow. So for freezing point depression, and what I'm going to do again is that I will go and do these calculations in a more straightforward way, forward it to your course rep, and he will now forward to you people to look at it. I will do some calculations with hand and then scan it and send it to you. Then you send it to your WhatsApp so that you can understand better. So freezing point depression. The question says, calculate the freezing point depression, right? Calculate the freezing point depression. Calculate the freezing point depression of a solution. Calculate the freezing point depression of a solution. Made by dissolving 20 grams of ethylene glycol. Ethylene glycol. Ethylene glycol is presented by this formula. I'm going to write for you. C2, that's capital C2, H6, capital H6, then 02, O2, sorry, O2, capital C2, capital C2, H6, O2, H6O2. That is ethylene glycol. Ethylene or ethylene, depending on how you want to pronounce it. But I pronounce it ethylene glycol. Ethylene glycol. That is the formula and the name. By dissolving 20 grams of ethylene glycol in 100 grams of water. In 100 grams of water. In 100 grams of water. And here, the change in freezing point depression is given as delta TF, just like in the slide. Delta TF is equal to KF, that is freezing point constant, KF times M times small m times small m times small m. As freezing point is delta TF, which is equal to KF times small m. Just like in the case of boiling point, KF is a freezing point depression constant. Freezing point depression constant. Our small m is known as molality. Molality. Don't bother, I will do all those calculations later in the night and forward to you with proper explanations. I'll tell you what is molality, the formula for molality and so on, how you calculate it. So M is equal to molality. M is equal to molality. Freezing point depression is change in TF equal to KF times small m. And I say KF is a freezing point depression constant. And small m is equal to molality. Now, how do we go about this? it is the same procedure. Okay? Molality is equal to, that is that small m. We want to find the small m, because for Kf, we know it. So in this case, the Kf is equal to 1.86 capital K kilogram/mole, MOL. It's not molarity, it's not molarity, it's molality. Don't confuse yourself. Molality is another form of this thing. Okay? M is molality, it's not molarity. It's molality. 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 Take note. Molality is different from molarity. It's molality. So, just like in the case of boiling point, we need to determine the molality, which is small m. And mind you, molarity is capital M, it's not small m. So there's a difference. So molality, small m, is equal to moles of the ethylene glycol divided by kilogram of water. So the next thing is 20 grams of ethylene glycol divided by the molar mass of ethylene glycol is 62. That is 20 grams divided by 62. The 62 is the molar mass of the ethylene glycol. So if you divide that by 0.1, mind you, you are converting the 100 grams of water to kilogram. So that will be 100 grams divided by 1,000, or 100 divided by 1,000. That will give you a kilogram. And the answer, that is small m, now will be equal to 3.23. 3.23. That is small m. That is the value of small m, 3.23. So now for you to be able to determine the change in freezing point depression now, that is equal to the constant, the freezing point depression constant multiplied by small m, which you got as 3.23. And the constant, that is Kf, is given as 1.86. Multiply 1.86 multiply by 3.23. Multiply by 3.23. So that will give you 6.01 Kelvin. That will give us 6.01 Kelvin. So water freezes at what temperature? 0. So the new freezing point, as a result of addition of that chemical, will be equal to 0 degrees Celsius. 0 degrees Celsius minus 6.01, which is equal to -1 degrees Celsius. So you can see that there is reduction 0.1 degrees Celsius. Okay, so that is the answer in the freezing point. Now, very quickly, let us calculate for osmotic pressure. And I told you that osmotic pressure is a pressure that is needed to prevent the free flow of solvent through what? The permeable membrane. And it's given by that. Forget about the long N2 over V RT equal to that and so on. Don't worry, you will not get confused. By the time we do face-to-face revision, you will not be confused. I'm very sorry, some of you are not chemistry oriented, but I'll force chemistry into your brain when we come for face-to-face revision. Don't bother about that. So now the osmotic pressure, I said, is the pressure that is needed to stop or prevent the solvent from passing through the permeable membrane. And mathematically is given by there's that sign like pi equal to capital C, capital R, capital T. Forget about the rest. Let's focus on capital R, capital C, capital R, capital T. Osmotic pressure. Osmotic pressure. Yeah, take this question very, very quickly. Very quickly. Take the question very quickly. Calculate the osmotic pressure. Just get the question. Even if we can't solve it, we'll solve it tomorrow morning. Calculate the osmotic pressure of a solution made by dissolving 5 grams. Calculate the osmotic pressure of a solution. Calculate the osmotic pressure of a solution made by dissolving 5 grams of sodium chloride in 1 liter of water. Dissolving 5 grams of sodium chloride in 1 liter of water at 25 degrees Celsius. At 25 degrees Celsius. In bracket 298 Kelvin. 298 Kelvin. That is 273 plus 25. We give you 298 Kelvin. You're converting from Celsius to Kelvin. Okay? And the hint there is that we should assume, right? Assume complete dissociation of the sodium chloride. Complete dissociation of the sodium chloride. In brackets, put I will explain. Put I equal to 2. That is complete dissociation. That is the ion. We are going to have negative and positive, completely ionized. Let's have 2 ionic stay negative from the chloride and positive from the sodium. So you have 2. So I equal to 2. Ionic constant equal to 2. So let me repeat the question again before the time goes. Calculate the osmotic pressure at 25 degrees Celsius, in bracket 298 Kelvin. Assume complete dissociation of sodium chloride, in bracket I equal to 2. So we'll continue tomorrow. But I will solve the problem and send to you tonight so that tomorrow we will not waste time on it. Do you understand? I'll do the calculations and send to you tonight with explanation